40 feet. That is how high the water could climb in Westport, Washington, and it could arrive in as little as 20 minutes. No highway, no bridge, no car is going to save you. By the time the shaking stops, the roads leading out of town will already be broken. So the people of Westport did something no American town had ever done before. They built a tower. It isn't a lighthouse or a decorative monument. It's a massive concrete platform sitting on heavy stilts, engineered to stand while everything around it turns to rubble and seawater. It's a place to run to when driving out of town isn't an option anymore. The reason they needed it isn't hypothetical. It's a fault line stretching across the West Coast that has ruptured before, will rupture again, and is well past due. Off the coast of the Pacific Northwest, stretching from Northern California all the way up to Vancouver Island, there's a huge rift in the ocean floor called the Cascadia Subduction Zone. It's about 700 miles long. This is where the Juan de Fuca plate is grinding underneath the North American plate, sliding down, locking up, and building immense energy like a tightly coiled spring. The last time it snapped, it triggered a magnitude 9.0 earthquake, probably bigger. That was on January 26, 1700. We know the exact date because of something bizarre that happened on the other side of the planet. On that night, a massive tsunami with no local earthquake attached to it struck the coast of Japan. Japanese records called it an orphan tsunami. Villages flooded, rice paddies drowned in salt water, and local officials logged every detail in ink, completely baffled about where a wave that size came from since the ground under their own feet never shook. 3 centuries later, geologists connected the dots. The wave that hit Japan had traveled across the entire Pacific Ocean from Cascadia. Once you calculate the travel time across the ocean, you land right on the evening of January 26, 1700. That is how scientists dated an earthquake that struck long before European settlers recorded history in that area. And the native peoples of the Pacific Northwest remembered it fine. Their stories were there all along. The Quileute, the Hoh, and the Yurok have oral histories describing the ground shaking, the ocean pulling back, and whole villages disappearing overnight. One account tells of a massive battle between Thunderbird and Whale that shook the land and swallowed the coastline. That wasn't just folklore, it was an eyewitness account of the last time Cascadia ruptured. So why should anyone care today? Because Westport sits right in the firing line, and the geography of the place is unforgiving. Picture the layout. Westport sits on a peninsula, basically a flat spit of sand sticking out into the ocean with Gray's Harbor right behind it. The highest ground for miles is barely above sea level. When the Cascadia earthquake hits, the entire coastline is expected to drop. The land sinks several feet instantly, meaning the ocean gets closer before the first wave even arrives. Then the tsunami hits. Estimates put the wave at 30 to 40 feet high. The real problem is the timing. For a town this close to the fault, the first wave could slam into the shore 15 to 30 minutes after the shaking starts. You cannot drive out in that time frame. Think about how those first few minutes actually play out. The shaking itself could last up to 6 minutes. That feels like an eternity when the ground is moving like a ship in a storm. You can't stand or run. Everything drops from the shelves. Power lines snap. And when it finally stops, you aren't on solid ground anymore. You're standing on liquefied sand. That's the part a lot of people overlook: liquefaction. Westport is built on saturated sand. When you shake wet sand hard enough, it turns into a thick liquid. Roads buckle and bridges snap off their foundations. The main highway out of town goes right through low, marshy ground, the exact terrain that turns to mush. Engineers fully expect those escape routes to fail during the quake itself, long before the water hits. So look at the situation. You have a few thousand locals, plus summer tourists. You have maybe 20 minutes. You have no high ground nearby, and your roads are destroyed. Where do you go? For years, there wasn't a good answer, and the locals knew it. That led to one of the most practical pieces of local engineering you'll ever see. The Ocosta School District had a major issue. Their elementary school sat right in the inundation zone. If a quake hit during school hours, there was no way to get hundreds of kids off the peninsula in time. So, in 2013, the voters passed a bond measure to rebuild the school and add something completely new to North America: a vertical evacuation structure. They finished it in 2016. The gymnasium was built with a reinforced rooftop platform sitting up to 55 feet above the ground, supported by massive concrete columns driven deep into the earth. It can handle the quake shaking and the force of the water, with room for well over 1,000 people on top. When the ground stops moving and the roads are gone, the plan is straightforward. You don't run away, you go up. It was the first one built in the United States. It took until 2016 for an American community to construct a vertical refuge like this, right on top of a school gym in a quiet coastal town. Of course, a school structure mostly protects the kids and staff. It doesn't help the commercial fishermen at the marina, retirees in RV parks, or tourists getting lunch on a summer afternoon. Westport's population swells in the summer, and a wave doesn't care who is local and who is just visiting. So the town kept going and built another structure, a public evacuation tower near the marina and beach area. Anyone can reach it on foot within a few minutes, head up the stairs, and get above the floodline. The approach is brutally simple. It accepts reality. It assumes the roads will break, the ground will sink, and the wave will travel faster than traffic. The only solution left is to get above the water right where you are. Consider the force involved. Water weighs about 62 pounds per cubic foot. A tsunami isn't a smooth surfing wave. It's a moving wall of ocean packed with sand, cars, crushed buildings, and debris. When that hits a standard structure, the force tears it apart. Normal wooden houses just get ripped off their foundations. A vertical evacuation site needs deep pilings so the ocean can't scour out the sand beneath it, open lower levels so water can flow through instead of knocking it over, and a deck high enough to clear the worst-case wave estimate with room to spare. The engineers had to design a building meant to take a direct hit from an ocean wave, get submerged at the base, get struck by floating debris, and stay standing. Zoom out, and Westport is just a preview of what the wider region faces. The Cascadia Fault stretches past Westport. A full rupture will impact Seattle, Portland, Tacoma, and Olympia. Millions of people live in that zone. Federal disaster models for a full margin rupture project, thousands of casualties, tens of thousands of injuries, and massive destruction. One official famously remarked that after a full Cascadia event, everything west of Interstate 5 will basically be ruined. Small coastal towns like Westport, Ocean Shores, and Seaside have the narrowest safety margins. They sit right on the edge, low to the sea, and easily cut off. For them, a tsunami isn't a hypothetical risk. It's a clock that could start ticking any time. The science behind this has been solid for a long time. Researchers established in the 1980s that Cascadia is a megathrust fault capable of a magnitude 9 quake. By the late 90s, the Japanese records helped fix the exact date of the last event. Geologists know these full ruptures happen roughly every 300 to 600 years, and it's been over 320 years since the last one. Estimates give about a 1 in 3 chance of a major quake on the southern section in the next 50 years, and around a 1 in 10 chance for a full fault rupture. Those are high odds for a natural disaster, yet actual construction of safety infrastructure has been slow across the region. A couple of towers in one town don't cover hundreds of miles of exposed coastline. Why the delay? Cost is a big factor, alongside how people process low-frequency, high-impact events. These structures cost millions of dollars, which is a lot for small coastal towns. Westport is built on fishing, local business, and tourism. Asking residents to fund heavy infrastructure for an event that might not happen in their lifetime is a tough sell. It's easy for people to assume it won't happen while they live there. Westport voted for it anyway. They looked at the map, realized they had 20 minutes, looked at their kids in the local school, and decided not to take the chance. They spent the money to give future generations a place to run. Think about what it looks like from the ground. Imagine you're teaching second grade at Ocosta Elementary on a typical Tuesday. Suddenly the room starts shaking violently. The lights swing, glass rattles, and the ground roars. You've practiced this, and you know what it means. The old strategy was mostly hoping for the best, hoping the roads stayed intact and that you could move hundreds of children to distant high ground in a few minutes. Deep down, everyone knew that wasn't a real plan. The new strategy is just a set of stairs. When the shaking stops, you bring the kids straight up to the reinforced roof of the gym and wait out the water. It isn't complex, but it works. which raises an obvious question. Why haven't more coastal towns done this? If you drive along the Cascadia coast, you'll see dozens of low-lying towns in the exact same position. Flat terrain, vulnerable bridges, and long evacuation routes. Many rely on basic warning signs pointing toward high ground that might be impossible to reach in time. It isn't a technical issue. We know how to build concrete shelters. It comes down to funding and priority. As a rule, communities tend to spend heavily on disaster recovery after the fact, but hesitate to spend on prevention beforehand. Cascadia gives no advance warning. There are no weather reports or tracking maps like you get with a hurricane. The shaking is the only notice you get. Everything needed to survive that moment has to be built years in advance. Westport put the money down. That concrete shelter might look plain, but it's practical. It doesn't rely on luck. It assumes the worst-case scenario will happen, that the land will sink, the roads will break, and the sea will come in, and provides a direct way up. The modern world relies heavily on the idea that basic infrastructure will hold when needed, that roads stay open and bridges stay up. Westport planned for what happens when those assumptions break down. Centuries ago, Japanese clerks documented a wave they couldn't explain. Native storytellers kept memories of past floods alive through generations. All that data points to the same reality. This event happens, it will happen again, and it leaves very little time to react. Westport built accordingly. Much of the coast is still catching up. When the fault finally breaks, survival will come down to a simple detail, whether a town built a place to climb or counted on roads that were never